During Tesla AI Day on August 19th, Ganesh Venkataramanan, Senior Director of Autopilot Hardware and lead for the Dojo project, revealed a hardware suite that is leaps and bounds beyond anything that is being used today, even in the highest level supercomputers. Not only does this hardware enable plug-and-play access to what will be the world's fastest AI supercomputer, it shows us what Tesla is thinking about for the future, both short and long term. Let's take a look at this astounding new hardware that will allow Dojo to awaken. For those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Hey y'all, it's Dr. Know-It-All. So a couple of things. First of all, I am not a hardware guy, but I've been around hardware long enough to know impressive when I see it. So there you go. Well, the other thing is you might think, well, man, you're a little bit late to the party on this whole Dojo thing because so many people have talked about it. But honestly, there are some issues with some specifications that people have talked about. We'll get to that later in this episode. But also, I want to speculate a little bit on what Dojo means for the future of Tesla and for all of us together. And so I think I can definitely add to the conversation. And certainly we are going to dial in a lot on the hardware. So you'll probably get more than your share of, really detailed stuff. Anyway, the speculation is later. If you don't really care about the hardware specs and stuff, I will put a break in the timeline so you can jump ahead to the speculation section. But I hope that this hardware coverage will be useful because there are a lot of details here, and I think it's super valuable for us to go over them in some level of detail, especially the smaller scale stuff that's really, really critical to how Tesla is using first principles to sort of reconstruct what the computer actually is. So let's just jump ahead a little bit and start with the specifications of the overall machine. I'm going to cover these so that when you listen to Ganesh talk, you'll have a bit more perspective. So first of all, everything is based on the D1 chip for Dojo 1, I assume. It's built on a 7-nanometer process. Each D1 has 362 teraflops of processing power. 25 chips are placed onto what's called a training tile, and 120 of these training tiles are assembled together to get over 1 exaflop. That's 1 exaflop of computing power. That is a big number. I will try to get all the zeros correct and put the number down here. I can't even keep track of how many zeros that is. I think 18 maybe? I don't even know. It's a heck of a lot of compute power. Anyway, this is going to be the fastest AI training computer by far, according to Tesla, 4 times faster than the competition. And note that this is an AI training computer. It kind of gets a little bit around the whole, how do you measure the fastest issue, what is the fastest supercomputer, et cetera. They say fastest AI training computer specifically. And I think with that metric, they are definitely going to win with this hardware. And of course, the last and perhaps most important specification is that this should all be operational by 2022 sometime. That's just crazy. So let's start off hearing from Ganesh's own words how he describes this thing.
My name is Ganesh, and I lead Project Dojo. It's an honor to present this project on behalf of the multidisciplinary Tesla team that is working on this project. As you saw from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer. And that's how we started Project Dojo.
I want to break in here and just say I love the fact that Ganesh says Elon prefetched this whole thing, right? Prefetching is compute speak for grabbing code you expect to need in the future to speed things up when you get there. So basically he's saying, Elon is the computer controller chip that was prefetching data. He's like, hey, we're going to need this in the future sometime, probably years and years away, because this is something that took a long time to build. And so he said, I need this. I'm going to hire the people to do this, give them the money, and turn them loose and make it happen. So that's super, super cool. And also, I think this clearly proves that Elon is not an alien, he's actually an AI. Or he's just a really, really bright guy who plans well ahead of time. All right, so anyway, back to it.
Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same time. So we thought about how to build this, and we came up with a distributed compute architecture. After all the training computers out there are distributed computers in one form or the other. They have compute elements in the box out here connected with some kind of network. In this case, it's a 2-dimensional network, but it could be any different network. CPU, GPU, accelerators, all of them have compute, little memory, and network. But one thing which is common trend amongst this is it's easy to scale the compute. It's very difficult to scale up bandwidth and extremely difficult to reduce latencies. And you'll see how our design point catered to that, how our philosophy addressed these aspects of traditional limits. For Dojo, we envisioned a large compute plane filled with very robust compute elements backed with large pool of memory and interconnected with very high bandwidth and low latency fabric and in a 2D mesh format. And on to this, for extreme scale, big neural networks will be partitioned and mapped to extract different parallelism, model, graph, data parallelism. And then a neural compiler of ours will exploit spatial and temporal locality such that it can reduce communication footprint to local zones and reduce global communication. And if we do that, our bandwidth utilization can keep scaling with the plane of compute that we desire out here.
All right, so why make Dojo, right? As he said, you need the best AI training performance. Right now, it takes forever to train very complex neural network models, and Tesla's building about the most complex neural network model out there. So you need to be able to train larger and more complex neural network models. You also need power and cost efficiencies because you can't run up the cost, you can't run up the power, etc. And you also just can't have things too big physically to fit in spaces. So all of that is really, really important. And as you'll be able to see, much of this comes down to space. You need to have no legacy silicon. You need to have extremely localized cooling, extremely localized compute, extremely localized bandwidth transfer. It comes down to physical scale. And that's really, really cool. So what's the issue here? In the abstract, it's fairly easy to imagine scaling compute power, right? You just keep adding more chips. But it's really, really tough to scale bandwidth and reduce latency when you put a lot of these chips together. And I think it's worth an aside here to ask what is bandwidth, because many people out on the interwebs seem to have this wrong. It's about how much data you can push around between and within chips, not how much each chip can process. They're very different things. The flops, or floating point operations per second, is a metric of compute power. The bandwidth, which he's measuring in like 4 terabytes per second bandwidth or something, is how much you can pass inside the chip or between chips. That's the difference between these two. So bandwidth has to do with data. You might imagine, it's like a fire hose versus a garden hose, right? A fire hose has a lot bigger water bandwidth. You can pass a lot more water through a big fire hose than you can through a tiny little garden hose. So imagine that when you hear bandwidth. Bandwidth is like having, a fire hose or bigger and bigger or something, right? It has to do with the size of the pipe for data to go through. So why does this matter? Well, at the macro scale, bandwidth drastically affects the perceived compute performance. Even if you have the world's fastest computer chips, if they're waiting on data, they're not doing anything at that moment except creating heat, right? So they're kind of useless. So on a macro scale, bandwidth is just as important as the raw compute power of each chip. And that actually brings us to what is latency. That is waiting for something else to happen. You could say chip 1 finishes its operation queue, and if chip 2 isn't done with its operations yet and chip 1 needs that, it just sits there and waits for chip 2's results, which slows everything down, even if each chip, again, is super, super fast. Or all the chips could be waiting for data to arrive from memory, right? So that could be a latency issue also. They could all say, like, give us more data. And, there's a dude out there drinking a Mai Tai, right? Metaphorically. He's going like, yeah, I'll get it when I get it, right? He's like, it's like a bartender at a little Caribbean bar or something, right? This guy is just like, yeah, I heard your order. I'm going to get there eventually, right? So that's latency, right? The people are waiting for their drinks and the bartender's just going like, oh, dude, I don't know. I think I've got vacation on the brain right now because I'm kind of doing 3 full-time jobs at the moment. So anyway, I would love to go to the Caribbean and just wait on a drink for a while. But anyway, so latency is waiting for other things. And that also has to do with bandwidth, of course. If you increase the bandwidth, then you're going to reduce certain kinds of latency. So all this stuff is tied up, but I think it's really important to understand what those things mean as we move forward and why they're so important. So anyway, in short, for supercomputers is not just raw processing speed that's important. And frankly, that's actually the easiest thing to scale up. But But data bandwidth and latency issues are just as important. In other words, just like with manufacturing in a factory, the slowest part slows the whole thing down, right? So if you've heard about that with Tesla manufacturing and them waiting on a USB cable or a chip or something like that and not being able to produce cars, same thing on the compute scale, right? You're waiting for something to happen and nothing else is happening while you're waiting. So anyway, a ton of the focus in Dojo is actually on the network fabric. So how do we get this? Well, we need a large compute plane. In other words, we need many of these little chip nodes together in a 2D plane, not a linear design. So that gives us high bandwidth and low latency. Also, we get to partitioning and mapping. So in other words, you can break big neural networks into chunks to process, and this is not trivial to do at all, and exploiting spatial and temporal localities. This was the massive news in my mind. Basically, they went back to first principles and they thought of the chip and the system as a physical object and designed everything necessary to be as close physically as possible to everything else. And this reduces everything possible to local zones of communication and computing. And in my mind, this is genius. By thinking of the physical object, they were able to design to take advantage of physical and temporal localities. All right, so that's the big picture abstract. Now let's get a bit more specific. How does Dojo remove these bottlenecks? In a 4-layered system.
We wanted to attack this all the way, top to bottom of the stack, and remove any bottlenecks at any of these levels. And let's start this journey in an inside-out fashion, starting with the chip. As I described, chips have compute elements. Our smallest entity of scale is called a training node. And the choice of this node is very important to ensure seamless scaling. If you go too small, it will run fast, but the overheads of synchronization and software will dominate. If you pick it too big, it will have complexities in implementation in the real hardware and ultimately run into memory bottleneck issues. Because we wanted to address latency and bandwidth as our primary optimization point. Let's see how we went about doing this. What we did was we picked the farthest distance a signal could traverse in a very high clock cycle, in this case, 2 gigahertz plus. And we drew a box around it. This is the smallest latency that a signal can traverse, 1 cycle at a very high frequency. And then we filled up the box with wires to the brink. This is the highest bandwidth you can feed the box with. And then we added machine learning compute underneath, and then a large pool of SRAM. And last but not the least, a programmable core to control. And this gave us our high performance training node. What this is a 64-bit superscalar CPU optimized around matrix multiply units and vector SIMD. It supports floating point 32, bfloat 16, and a new format, CFP8, configurable FP8. And it is backed by 1.25 megabyte of fast ECC protected SRAM and the low latency, high bandwidth fabric that we designed. This might be our smallest entity of scale, but it packs a big punch. More than 1 teraflop of compute in our smallest entity of scale.
So let's start with chips. We're going to start with the smallest unit that he talked about. We'll begin with the training node, which is based on the largest physical distance that signals can travel in 1 clock cycle, which is somewhere around 2 gigahertz, although they don't exactly say what that, they do say that they ran it at 2 gigahertz in a test bed situation, but they don't say what the maximum clock speed is. But anyway, whatever that is, they built this thing designed so that light speed in a wire basically can travel through the chip in 1 clock cycle. So that was their physical limitation on that. And again, that was genius to start with that. So they take that square and then they fill that with signal wires to increase the bandwidth as much as possible. And then you place your processing units like matrix multiplication, parallel processing, registers, etc., so that you build your chip upon the physical constraints of signal speed. Also note that a big chunk of SRAM, 1.25 megabytes, is placed directly on each chip so that memory fetching is fast, like prefetching, and there's also a scalar CPU on each chip as well, which makes the chips much more than GPU-like chips. In other words, they're more flexible and they can act more in a standalone autonomous manner and be programmed. So from this image, you can definitely see that Tesla is specifically focused on integers and matrix multiplication, which is very much like a GPU, but the core is complex enough to function as a CPU, which gives the chip the best of both worlds. Also note that they use SIMD, which is single instruction multiple data. This is not groundbreaking, but basically it means they can act on many data elements in parallel at each instruction step. So in other words, it's just faster. And then they add a simple CPU, a scalar multi-threaded CPU that gives it enough power to basically be programmable and to be quite useful in a flexible manner on the individual node level. Also, fascinatingly enough, it supports a new numeric format that I hadn't heard about, configurable floating point 8. It sounds like it's some sort of optimized floating point storage mode, which is really, really cool. Again, I don't know what it is because this is the first time I've heard of it, but basically floating point itself is great, but it's somewhat limited in terms of precision when you have low bit depths. So this configurable floating point might actually be a great way to utilize low bit depths and still get very high precision calculations out of it. So anyway, this chip can do 1,024 gigaflops or 1 teraflop in CFP8. So wow, like holy crap. That's on a per chip basis. And they get 512 gigabytes per second of data flow on either axis. In other words, either cardinal direction. That's pretty impressive. Also note that the architecture is optimized for machine learning kernels. Specifically, that's for like small chunks of convolution kernels or other things that have to be calculated as fast as possible over and over and over again. These are truly astounding numbers. But wait, it gets better.
And even in the physical realm, we made it extremely modular, such that we could start abutting these training nodes in any direction and start forming the compute plane that we envisioned.
In other words, what Ganesh is saying here is that these chips are effectively Lego blocks. You snap them together and you don't have to worry about any of the overhead normally associated with putting chips together, because all of that overhead, all of those elements are already physically located within the chip. So now let's start building the macro chip based on these nodes.
When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power SerDeses, 576 of them, to enable us to have extreme I/O bandwidth coming out of this chip. Just to give you a comparison point, this is more than 2 times the bandwidth coming out of the state-of-the-art networking switch chips which are out there today. And network switch chips are supposed to be the gold standards for I/O bandwidth.
So we're going to put 354 of these training nodes together, and you're going to get 362 teraflops. Holy crap, right? You then surround this 354 chip node with a ring of 4 terabyte per second bandwidth communication hardware. In other words, it'll talk to any other chips at super, super high speed with no other hardware needed. And as Ganesh said, this is 2 times the bandwidth of state-of-the-art networking switches. State-of-the-art networking switches, that's their job, right? So this is just amazing. They're outperforming things that are specialized to do this particular job in a computer where that's just part of what they're doing. And so you build this out and you get the D1 chip for Dojo 1, I assume, which is essentially like the Intel Core i7 of the Dojo supercomputer, although that's a terrible comparison because this thing is so much more powerful. But that's basically what it is. It's like the heart. If you open up your motherboard or whatever and you see the Core i7, the Intel chip or whatever chip it happens to be sitting there, that's effectively what this is, and it's approximately the same size. It's just insanely more powerful than something like a Core i7 chip. I also want to make a note for later discussion that he does not mention who is making this chip. So anyway, this is clearly a macro chip that he can hold in his hand, and it's built on 7 nanometer technology and constructed and operates as an independent unit. It's 645 millimeters squared. In other words, it's about that big. And it does 362 teraflops at CFP8, or 22.6 teraflops for floating point 32, which is still screaming fast. It has 50 billion transistors on it, which is insane. insane. And it does 10 terabytes per second on-chip bandwidth communication and 4 terabytes per second off-chip bandwidth communication, in other words, to other chips. And this thing only sucks down 400 watts of power, which is insanely low for this kind of performance. In other words, it's like 4 of those old 100-watt light bulbs. And something that I think is just amazing is there's no legacy support on this. They built it from scratch. In other words, if you compare this to Intel chips that have tons and tons of legacy gates that weigh space, gates, and power, this thing is just maxed out to be as modern as possible. Very, very cool. Similar in some ways to the Apple M1 chip, which I did some episodes on above if you're interested in that. But basically, they're just designing this from the ground up and getting rid of a lot of junk that's just sort of piled up over the decades. So anyway, the D1 is as powerful as a GPU, as flexible as a CPU, and the bandwidth or data transmission is better than the best networking switches. In other words, what the this is the kind of thing you get from building computers from scratch. So I think this image is amazing, right? Just look at where Dojo is on the compute power versus bandwidth scale. It's a whole other level. It's like playing in its own, field, right? You've got all the little pee-wee leagues playing, and then you've got the professionals out there playing. And remember here again that bandwidth is absolutely critical. Recall that Andrej Karpathy, and I've done some videos on this, he talks about having petabytes of data that needs to be trained on petabytes, right? So you've got to just move massive amounts of data through this thing and compute on it in order to train in an efficient manner. And so that's why this is all so crucial, and that's why all of these aspects have to balance out with each other. So right, all of those petabytes of data have to be passed around these chips, and if you're waiting on the data, you're not calculating even if the computers are super, super fast. So that's why the bandwidth is so critical here. All right, so now let's talk about the system of putting all the chips together. It's crucial to see how the design of the D1 actually enables all of the higher level aspects of Dojo.
How to design the system around it? Let's see. Since D1 chips can seamlessly connect without any glue to each other, we just started putting them together. We just put $500,000 training nodes together to form our compute plane. This is 1,500 D1 chips seamlessly connected to each other. And then we add Dojo interface processors on each end. This is the host bridge to typical hosts in the data centers. It's connected with PCI Gen 4 on one side with a high bandwidth fabric to our compute plane. The interface processors provide not only the host bridge, but high bandwidth DRAM shared memory for the compute plane. In addition, the interface processors can also allow us to have a higher radix network connection. In order to achieve this compute plane, we had to come up with a new way of integrating these chips together. And this is what we call as a training tile. This is the unit of scale for our system.
So as Ganesh says here, they put 500,000 training nodes together, or in other words, 1,500 D1 chips, which consists of a lot of training nodes per chip. And you snap all these together just like snapping Legos together. No, massive infrastructure you have to build or anything like that. Just go click, click, click and put them all together. And as you might imagine, if you've seen other supercomputers, this is totally different from them. They require massive, massive infrastructure to work, and you see cables everywhere and all of that kind of stuff and massive cooling and so forth. So this is very, very different from the ground up. And then around these groups of chips, you place interfaces, memory, and communication hardware around this training plane for communication with the outside world. And then you go 3D for the communication elements and create a training tile out of all of this. And then you combine 25 of these D1 chips into a larger compute cluster, the training tile. You put on the cooling, the memory, and other architecture and create a fully independent unit that can be plugged into power and memory and compute like crazy.
This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training tile. And this tile gives us 9 petaflops of compute with a massive I/O bandwidth coming out of it. This perhaps is the biggest organic MCM in the chip industry, multi-chip module.
So this training tile gives you 9 petaflops on this one tile and 9 terabytes per second of communication bandwidth to the outside world. I mean, good Lord. This is the biggest MCM or multi-chip module in the industry, according to Ganesh, and I can't imagine anybody saying that that's not the case. And what's even crazier here is that Tesla actually had to build the machine to build this machine. In other words, no hardware and software tools existed to build these tiles, so Tesla just had to do it themselves.
It was not easy to design this. There were no tools that existed. All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality.
But what about the massive power needs of these training tiles? Well, again, you think 3D, not 2D.
Now that we had our compute plane tile with high bandwidth IOs, we had to feed it with power. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here. But we didn't stop here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. Our compute plane is completely orthogonal to power supply and cooling. That makes high bandwidth compute planes possible.
Note here that power is flowing into the bottom and heat is flowing out of the top. And if my calculations are right, it's about 936 kilowatts of power these things are able to produce and 15 kilowatts of heat rejection. So it's just kind of crazy stuff. From close up, of course, these tile images show what appears to be liquid channels, and I imagine this thing has to be liquid cooled. I just can't imagine it's air cooled. It would make much more sense, and again, it looks like from all the images I've seen that these tiles are actually liquid cooled. So with all of this, we get 9 petaflops of compute power and 36 terabytes per second of bandwidth per tile. And this thing is actually real, as in it's already been built and they've run some test code on it. Amazingly enough, when he talks about this, he says it's really hot off the press. Like last week, they started running this thing at 2 gigahertz without the maximum amount of cooling. And look at the performance. The green dots show Dojo with limited cooling, so it's underclocked, running GPT-2. It's just astounding to see these kinds of numbers here. But hey, one training tile isn't enough. Let's make it a cluster.
How to form a compute cluster out of it? By now, you must have realized our modularity story is pretty strong. We just put together some tiles. We just tiled together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this, we have an exapod. This is 1 exaflop of compute in 10 cabinets. It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node, and there are 1 million nodes out here.
So in a traditional computer cabinet, you can fit 12 of these tiles, 2 by 3 by 2. And that gives you 108 petaflops of power per cabinet. But screw cabinet walls, let's just plug them all together. And what do you get? you get the exapod. In other words, you get 1.1 exaflops of compute power using CFP8 using 120 training tiles or 3,000 D1 chips, or alternatively over 1 million training nodes. Again, all of these numbers are just kind of mind-boggling. So that's the hardware from the smallest unit up to the biggest that they use. But finally, let's touch on the software for a moment.
Not just the hardware, the software aspects are so important to ensure scaling. And not every job requires a huge cluster, so we planned for it right from the get-go. Our compute plane can be subdivided, can be partitioned into units called Dojo processing unit. A DPU consists of one or more D1 chips. It also has our interface processor and one or more hosts. And this can be scaled up or down as per the needs of any algorithm, any network running on it. What does the user have to do? They have to change their scripts minimally. And this is because of our strong compiler suite. It takes care of fine-grained parallelism and mapping the problems of mapping the neural networks very efficiently onto our compute plane.
So the software is pretty amazing too. For one thing, they can subdivide the massive compute power into DPUs or Dojo processing units for smaller jobs. These are virtual compute nodes that can be spooled up to match your needs. And see the speculation later. But how hard is it to change from traditional PyTorch using a GPU to using Dojo? Well, it's super simple. You basically change one single word and it just works. This is literally insane. This is a supercomputer at your disposal simply by changing one word of code. I mean, this is something that researchers are absolutely salivating for already, and I'm happy to be the front of the queue, if I can be, to try to use this as a researcher someday when they release this, software as a service kind of thing. Anyway, it's just completely nuts that you can basically just change one thing in a parentheses and the whole thing just works on Dojo. That is brilliant software execution. So they've designed Dojo to be so simple to transfer to that any researcher anywhere can access its power simply by changing that line of code in their software. So that's Dojo's hardware and a bit about its software. How utterly brilliant its modularity is, how small and relatively non-power hungry it is, and how easy it's going to be for anyone to use. It's got 4 times the performance, low cost, 1.3 times the performance per watt, and a 5 times smaller footprint, all due to a redesign from the ground up. But what about the things that Tesla didn't say at the presentation? It's speculation time. So just to make a very clear note here, what happened before is all stuff that they talked about. What's happening next is all from my brain, right? So do not hold anyone else to this. This is just on me and it's all just speculation. So the first thing I want to talk about is who is building this chip, right? They talk about it a lot, but they don't say who's building it for them. Is Samsung building the chip? It seems kind of odd that they didn't join the event and advertise this, right? Is TSMC building the chip? Same thing. But what if Tesla has bought or built their own fab and is actually making these chips themselves? This seems crazy, but it actually makes sense. For the future and being vertically integrated and to help with the global chip shortage, it would be best for them to make the chips themselves. But how do you start doing this, right? It's a massive multi-billion-dollar investment, and trying to churn out, millions of these chips immediately is crazy, right? But Dojo only needs in the thousands of these chips, not in the millions needed for general computing purposes like full self-driving hardware, airbag controllers, and whatnot, right? So you can start here like kind of almost like a pilot plant, and you can get good at building the chips yourself. And you also don't have to worry about selling these chips to customers, right? So the cost per chip is not a huge issue at this point. What's super important is gaining experience and enabling a future higher production fab that will be critical to Tesla's long-term success. And we already know, of course, that Tesla does nothing if they don't plan for the future. So anyway, my speculation is that Tesla is actually building these Dojo chips themselves right now. And why are they building these Dojo chips? Well, for full self-driving training, duh. But they could do this with the current hardware, and they are, obviously, since Dojo's not working yet. So even with their current supercompute cluster, full self-driving can be better than humans right now, in the future as they keep training, but using their current hardware. But number one, if you want to chase those nines, then Dojo is needed as it vastly speeds things up. So if you want the 99.999999% safe, it's important to have a much, much faster compute cluster that works much better. But number two, we have, of course, as Tesla talked about, the Tesla bot, which is going to need even more of this training stuff. And 3, we have simulations, which I've talked about up here, and other corollary functions that could use this training, or at least they could use the older one full-time if the full self-driving training can be done on the new Dojo computers. And of course, as I mentioned, this can all be used for software as a service. In other words, you can sell this to other companies, universities, etc. So there's a huge potential profit center there. And again, we know Tesla plans for the future, so this would make a lot of sense that they're building this for the future of their needs, not for the present of their needs. And finally, what about full self-driving hardware 4 or full self-driving computer 2 that will be running your Tesla in a couple of years? Well, I'm going to make a prediction. Either hardware 4 or full self-driving computer 2, as Elon's calling it now, will be a modified D1 chip, or the next generation will be. Let's think about this. The individual chips are very small. They're about the size of hardware 3 chips, and they're very low power already. And with DPU or Dojo processing unit, one can make virtual full self-driving computers on the Dojo supercomputer and actually run the code on these virtualized versions of the car's hardware to tweak the exact design to get it kind of dialed in. And that's pretty amazing to think about, that they could actually be designing these chips and modifying them and tweaking them on the supercomputer, kind of running them in little sandboxes as if they thought they were the real full self-driving computers. So how would this actually work? Well, you could either run this chip at very low clock speed, or you could create something like a half-size version with no external bandwidth, silicon and stuff, that can run at around 50 watts rather than 400 watts, and you can swap this out basically for the hardware 3 that's in the cars right now. So if Tesla got this lower power version running, it might be able to do something like 100 teraflops in it, right? At around 50 watts per chip. And of course, remember, you need 2 chips for redundancy, so that's around 100 watts total for the board, which is about what we already have today. So that would give you 100 teraflops per chip in your car, which is completely insane. Now, remember, of course, this is rough off-the-cuff calculations and speculations, so don't take that particular number too seriously, but still, anything in the ballpark would just be crazy. And even better, all of the trained neural network models that they're working with on Dojo could likely flow into these chips with a whole lot less refactoring than has to happen today. And they could be running full self-driving at crazy high frame rates on your car, and Tesla can make these themselves, assuming my point above. So if you imagine after they build Dojo, by this time they're good at making these particular kinds of chips, so they can ramp this and they can start making them by the tens of thousands per week. Again, as I said before, this is all speculation, but given the insane prowess demonstrated by Tesla hardware at AI Day, I'm pretty convinced this is going to happen in the next couple of years. At which point, by the way, Tesla might actually have to register their cars as national security level computers with the US government. How nuts would that be? Even without considering the future possibilities, what we saw at AI Day was astounding. Even though I'm not a hardware guy, like I said, I can appreciate how difficult this was and appreciate how genius it was to go from first principles, ground up, and remake these chips to suit their needs. Long-term vision and the cojones to stick it out and do whatever it takes to make the vision come true are what sets Tesla apart. And really, no other company on the planet can manage this level of hardware and software prowess. The world is becoming Tesla's playground. Let's see what they can do with it. All right, I hope you enjoyed this episode and found it fun and informative and a bit intriguing. If you did, definitely like it so other people can find it. And if you enjoy this kind of stuff, definitely consider subscribing, especially because I've still got either 1 or 2 more episodes on AI Day still to go. It's just taking forever to get these all done. But anyway, I promise they're super worth the wait. So definitely subscribe so you can check out those when they come out. As always, a huge shout out to my patrons on Patreon. Thank you all so much for all of your help, all of your support, all of your goodwill. I really do appreciate it, and thank you. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And if you're interested in some awesome merch, check out the link in the description. We've got the Tesla Bot t-shirt, which is super popular these days. Don't mess with Tesla. Lots of other t-shirts, tumblers, mugs, etc. So check out the link in the description and help the channel out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a new car, a solar roof, a power wall, or anything on Amazon helps out the channel. And as always, feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.